we go. So we'll flip things around, right? While the stuff is downloading, we will talk about the concepts involved in move that over. The concepts involved in buffer overflow attacks, right? So did either of you guys watch that video on buffer overflow attacks I posted? Yes, no?
No, I didn't.
Okay.
Is it in Slack?
Which one? No,
thought
I
I
don't
posted
think
it to
not
Slack.
yet.
I can let me verify. It would have been. You know what? Maybe I didn't hear. Maybe I just posted it to the Cybersecurity Club. Or should we not to the Cybersecurity Club, but to the oh, you know, I didn't have it there either. So I just sent it to, because I invited computer science students because this is a programming type topic. And with them, I included a video. That's okay. I'm going to go over the same stuff. So let's talk about how a program works. Right? Got to put on my drawing glove. So oh, there it is. Let me go ahead and, why do I keep losing? This is harder than I thought. Click that right there. There we go. There we are. All right, so what runs instructions on your computer? Not a trick question.
Binary.
But what runs the instructions? The CPU, right?
Yes.
So the central processing unit. The central processing unit contains a whole bunch of registers. And these registers all have names. You know, we're going to be looking at EIP, you know, EAX, whatever. There's a whole bunch of these registers, and essentially what the CPU does is it takes values from registers, which hold those binary numbers, and it sends it to something that processes it. There's a special segment of hardware that does addition. There's one that does multiplication, right? There's one that does a if statement. So it looks, if this one's bigger than this one, it'll change the command over here. And then down here, there's a special register which holds whatever the current command is, right? The CMD, right? Whatever that current command is. You guys with me so far?
Yeah.
Okay. So I'm going to actually, I could probably find an image that will demonstrate this better than I could. C compile assembly. Let me see if I can find an image of this. All right, let me move this. So if you have a program like this, right? So this is, have either of you guys done any programming classes?
No, I haven't.
Okay. Catherine? Have you done any?
No,
Okay. So this just says
no,
we're defining an array size of 4. We're setting aside 4 bytes, right, for characters. And then we have a main function, which is going to declare an integer I, and as for I is 0, while it's less than 4, because we set that to 4 up here, we're going to keep increasing it. And then we're just setting the value of that index of the array to 0, right? So we're just setting aside 4 bytes of memory and then setting them all to 0. That's all this does. A very simple set of code. And then that would compile to assembly, which would look something like this, right? Human beings don't normally look at assembly and figure out what's going on. This is too complicated for us, right? We're much better at, let me move this over a little bit. We're much better at the code. So we write in a higher level language, and then we compile to assembly, and then that assembly is turned into machine code, which actually runs on the machine. Does that make sense so far?
Yeah.
Okay. Now, when this happens, when it's turned into that machine code, there's a certain pattern. I'm gonna move this over here. Now let me do this. There's a certain pattern that is used, a certain layout for the memory. So you can think of the program and all the instructions. Ooh, that's not what I wanted. You can think of it as like a big long strip. I am really bad at drawing straight. I'm going to undo that. Ooh. This is why I'm into computers and not art. All right. So each kind of, if we think of these as lines, each line here is one instruction or piece of data or something. And our addressing, typically at the top, we're talking about F, 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 and then something. And then at the bottom, we're talking about 0, 0, 0, 0, and then whatever. So we're counting from low to high as we go up. And we always write it in hexadecimal. So we write FFF, instead of, I don't even know what that would be 65,555, I think. I'm not 100% on that. But that's kind of how we lay things out, right? And then each of these is a section, right? That is, there's a certain segment and certain types of instructions or data go into that segment. So at the very top, we have the kernel stuff. What's the kernel? I know you guys took COSN 5. What's the kernel?
The computer program at the core of the system.
The core of the operating system, right? So only the kernel instructions are, it's really not the whole kernel, it's just our calls into the kernel. So if you want to save a file, if you want to draw something on the screen, if you want to talk to the network card, it all has to go through there. So those are instructions that call to the kernel. And then we have the stack is the next section. And then the stack grows down. That's the key thing to understand about the stack. Then down here we have the heap. And then the heap grows up. And none of this is to scale or anything, but I'm just giving you an idea of the relative locations in memory. So if you've ever, you guys have, neither of you have written code before, but if you're in like Java or C++, if you ever use like the new keyword, if you say like new int x, that means I want you to have a variable named x, and I want you to put it on the heap, right? The stack is every time you call a function. So if you call, func, and it has int x, when you call it, that x is going to be placed on the stack. And so every time you call a new function, you grow the stack down. As you return from those functions, the stack goes back up. The other thing that goes on the stack every time you do that is the return value. That is, I called this function from somewhere in the code. I put the return value on the stack so that when I'm done, I jump back to it. That's important because that's the thing that we're going to end up overwriting in order to manipulate things with our buffer overflow attack. And again, so this is all concepts so far. Underneath the heap is what we call the data. And data is for global variables, right? If you have variables that everybody's going to need access to, it goes into data. And underneath that is called text. And text is the actual instructions of your code. So we were looking over here, all of this stuff will go into the text portion, right? So every time you compile a program and then it's an executable or whatever, you double click on it and it starts running, this whole thing happens. All of this gets laid out in memory, and then there's some starting point in here. Let's say that it's this. Let's say that it is instruction. I'm going to make it 0x 00 80, right? That's your starting point. It's going to be different. So it starts by executing that instruction, and that instruction will tell it, hey, put something on a heap, or hey, start this function, or whatever it's going to do. And then the next instruction is going to be, what do you think the next instruction is going to be? 0x0084, right? So it keeps going up every time. That's the instruction address that gets loaded onto the CPU. The CPU does whatever it says, and then you continue on. Again, this is a very high level approach. You don't need to really be master programmers to do a buffer overflow attack. You just need to kind of understand the concepts that we're dealing with. Does this make sense to you guys?
I've done a buffer overflow type thing with one of the NCO challenges one time.
Okay.
I had to use GDB.
Yep.
And then I was familiar with it because Vince taught me how to do it, and then I just get to this one point where you type a bunch of words and it stack smashes, and then outputs the flag. Yeah.
And what we're doing is similar. We won't use GDB because we're doing it in Windows, which I don't remember that challenge from NCL.
Sorry. It was from. I did Cyber Fast Track.
Mhm.
It was through SANS. It was one of the challenges.
Yeah, so you would see buffer overflow there for sure, right? Yeah, you would definitely see buffer overflow there. There's a lot of capture flags. So you will start to see it now, and it's the reason you do buffer overflow is the truth is that the attacks we're going to do today would not work on any modern system. Your operating system has things that will defeat this. But the concept of what we're doing is the same as every vulnerability that anybody finds, right? You know how like every time you open up Adobe Acrobat, it's got an update for you to install, right? That's because somebody figured out another attack similar to this, right? That is based on the same principles that can take over your Adobe Acrobat reader. Did you guys watch that video I made on the Signal Celebrate thing?
Yes.
I have not.
Okay. But that post
neither.
the blog post by the president of the CEO of Signal, basically saying we hacked Celebrate, so don't mess with us. What he was doing was a type of buffer overflow attack, right? You have untrusted data coming in, and I'm going to make it do things that you don't expect, right? That's what it is. So that's what we're doing here. So what I want, what I'm looking for in a buffer overflow is there any code here in the text where I can input information? With your capture the flag, that's always going to be over a network, right? And that's how I'm going to show it to you. But if you look at like Celebrate, the Signal Celebrate thing, what they found was Celebrate is grabbing all these files. Well, what if I put a bad file in there, right? What if I, what if I put a file in there? What if, there's a weakness in Adobe Acrobat Reader and I give you a PDF that exploits that? So somewhere in there, there has to be a way that you ask for data from me. And when you read that data in, where's it going to go? The stack, right? Or sometimes it goes on the heap. But what I'm hoping is you're going to read in my data and I'm going to give you my fake bad data. Maybe it'll come on the heap here. And that's going to grow up. And if I can overwrite this return value, right, and put in that return value whatever I want, boom, I'm going to make you run my code, right? Because I can say the return value points over here, and this is my reverse shell. This is my virus. This is whatever I want you to run. So conceptually, it's really easy. At some point, you're taking in untrusted data. You're not stopping me from writing as much as I want. If I can figure out exactly how many I can write in till I hit that return value, right? Then I can redirect it to whatever I want to redirect it to. So do these concepts make sense to you guys? Yes, no?
Or yeah.
Okay. I mean, I know we haven't done anything with them yet, so it might not be specific enough, but I want you guys to, to understand what it is we're doing here. With that in mind, now, Vince, did you download all the virtual machines that I indicated?
Yes, I have Brainpan running. Yep.
Okay, good. So you're going to, extract the WinDev, right? You're going to extract Brainpan, and then you'll have those two folders there. Then you will fire up your Oracle VM. Since we all have Kali, I'm not going to import that one. I'm just going to, actually, I think this is the Kali I've been using. So I'm just going to go to File, Import Appliance. I'm going to browse to, and again, mine is on my D drive. So I'm going to go into Brainpan and import the Brainpan OVA. Click Next. I'm going to leave all of these the default. In particular, where's the, yeah. So I'm going to click Import. All right. Now, one thing I'm going to click on Settings here, and I want to point out on the network I'm on bridged adapter. That works the best, but there are other ways. You can put them both on the same internal network and get them talking, but just remember that Brainpan requires a DHCP. It has to get an IP address. So now I'm going to go ahead and click Start, and Brainpan will start up. I'm going to take off my drawing glove, my Michael Jackson glove. I'm going to move my pad out of the way. And eventually, by the way, you could just do, because you never actually interact with Brainpan, you could just do a headless start, but I always like to do the regular start so that I can see if it boots up correctly. Like I'm not seeing anything now, that bothers me. Remember, right control will get your mouse out of it if it gets stuck in there. All right, I'm going to let that keep going, and I'm going to go ahead and start up my Kali. Which I have very large. So I'll make that kind of fit the screen for you guys. If I can get my mouse back. All right, there we go. I'm going to log in. And it bothers me that I don't see anything for Brainpan here. So I'm going to go ahead and restart this machine. And let's see if I get something.
Just now, you said something about DHCP. Where do I see that?
Okay, so
in settings?
in the directions for the Brainpan
Professor?
machine, yes, I'm in the directions for the Brainpan machine, it tells you it needs DHCP. Now, that is built in by default in some parts of VirtualBox networking. So as long as we use the bridged option, as long as everything's on the bridged option, it should get an IP address. It's bothering me that I'm not seeing anything right now. But let me test and see if I can find it in Kali. So how would I find it?
Okay, Brainpan.
Nmap. There we go. So if I look at my IP address is 192.168.254.106, right? So that's the network that I'm going to scan. So I'm going to do Nmap, right? -SP is a ping scan, which means I'm just pinging stuff to see if it's there. And I'm going to do, because I've already done this before, right? Z Shell is giving me suggestions. So in your Kali machine, when you do IPA, you might see something, your IP address will be based upon your local network scheme. So mine is 192.168.254. Yours might be something different, but conceptually it'll be the same. So if I do that, it starts scanning stuff. And so you see it found, I don't know, it found my hub, it found my Chromecast. I don't know what this is. Don't know what this is. This one's unknown. Found my Raspberry Pi. This is itself. And then it found Brainpan, right? So it looks like Brainpan is running. And its IP address is 192.168.254.111, which is good. So now what I want to do is I want to scan that. And with buffer overflow, if you know it's a buffer overflow attack, you're going to want to check all ports, right? So normally I always start with with a top port with a scan, but with buffer overflow, it's almost always some crazy port, just because of the way that it works. So just do Nmap, and then 192.168.254.111. And I could specify all ports. Actually, let me do -P. All right, because I know what ports this is. I'm just going to do -P 0 to 20,000. Oh, it helps if you put the right IP address. There's nothing on the 193. Okay. So in scanning it, I found two open ports, 9999, and it says the service is named Abyss, and 10,000, which is SNet sensor management. All right. What would I do next? General hacking. Go to them, check them out in a web browser. That's what I would normally do, right? And eventually, So if I do 192, all right. So if I go to the 9999, oh, I get something kind of weird. This doesn't look right. Can I type anything in? I can't type anything in, but okay. Let's try the 10,000. Are you practicing safe coding? So this is some kind of page. All right, so it looks like port 10,000 has a regular web server. Port 9999 is something else. I want to investigate the something else a little bit more. What is the Swiss Army knife of networking? Netcat, right? Netcat. So generally my next move would be, let's just try to just raw talk to a port with Netcat. So Netcat 192.168.254.111, and then the port that I want to talk to, 9999. Okay, and this is what we saw before, right? So it's just sending me raw text. So you're getting error invalid HTTP response. So that might be Vince, that you're using a more up-to-date web browser than I am? Well, I'm in Firefox, right? So it's clear when I connect to it with Netcat, it sends text to me, right? So when my web browser got the text and said, oh, I'm going to just display this as text. Your Chrome browser is getting the text and saying, wait, it didn't say HTML. It didn't have that encoding at the top. I'm not going to accept this. But it says, welcome to Brainpan, enter the password. I'll just put in password and my access is denied. But what we have here is a network application, right? That I can put data into. I can send data to. So now we have something. So now I kind of see where, okay, now I have an opportunity to execute a buffer overflow attack. However, I don't have a copy of it yet. So let's kind of bounce back and take a look at that port 10,000. If I'm going to investigate a web server, what's the tool I'm going to use first? Straight NCL here. Derb or Derbuster. Yeah, burp is actually more advanced. But the first thing I always want to do is let me just do a quick scan. So I like derb because it's command line based instead of derbuster. And I'll just do derb http://192.168.254.111:10,000. And it just takes the quick word list and it finds index.html, which is the page that we were just looking at, and it finds a directory called /bin, right? So let me go ahead and take a look at that directory. And you'll find this fairly commonly in capture the flag, what do you call it? Buffer overflow, because they don't want it to be hard to find a copy of the executable. As a matter of fact, a lot of times they just give you a copy of the hey, here's the executable, here's the machine it's running, and here's the network connection. This one, because they gave it to you through Vulnhub, you do have to do a little bit of digging to find the executable, but you find it, and then you click on it and you save it. And then, oh, this is the other thing. You have to have in order to get that file out of it. Let me go ahead and I'm going to minimize my thing there. If I go to my folders, if I go to downloads, we can see that I did it in the past. Let me go ahead and cut that. Oh no, let me go ahead and delete it. Here's my Brainpan. So I have to get this off of my machine. I forgot to mention this before. Under settings, under advanced, you can have your clipboard, which clipboard doesn't, right-clicking and copying doesn't always work. So it's better to, I think it's better to use drag and drop, right? So it has to be turned on there. And if you don't have it on, you're going to have to stop your machine to turn it on. But once it's on, then you can drag Brainpan onto your desktop. And then it will be there. And then we're going to be able to drag that onto our Windows machine, right? And once we have it on our Windows machine, we have an environment where we can start poking at it. Let me go ahead and minimize this. Let me go ahead and minimize Brainpan because I don't need that right now. Let me go back here. So Vince and Lazaro, you guys are just joining us. Earlier, we had that windev eval.zip, and we extracted it. Have you guys both extracted it yet? Okay. So once you extract it,
The Brainpan, but I can't get it to work.
okay, you kind of faded out there, Catherine. Can you say that again?
I got the brain extracted and loaded in the virtual machine, but for some reason it's not working. I don't know what I did wrong.
All right. I'm going to take a look at yours in a second. For right now, though, let me show you the process for
Okay.
importing that Windows machine is just the same. Once you've extracted the zip file, you'll do File, Import Appliance. You will browse to, mine is under D, the Windows Dev Eval, select it, open it, click Next, import it with default settings. Now this is going to take a couple of minutes while that goes on. So while that's happening, Catherine, can you please share your screen so we can take a look at what you got going on?
Okay, give me 1 second. Some reason my machine froze. I think it's because it's downloading.
It could be that, yeah, the download that you have going on is
Right
taking up your
now.
bandwidth.
Give me 1 second. Yeah, I'm gonna pause it. It's totally frozen. Doesn't even let me
Nope.
do anything.
Catherine, try right-clicking on your download and saying pause.
You can go ahead and start without, just so I can share. Oh, I was both of them already. So I'm going to go some of the browser. Some you just here.
Well, Jason, we've been working on kind of getting everybody set up. So we're talking about importing the VMs and things. We did start a little bit, but we can go back and review that because we're still getting Catherine's Brainpan up and running.
Okay.
So Catherine, did you say your download finished or you paused it?
No, I pause it. I'm trying to share my screen now. Come on.
It's okay. If it takes a little time. Those networking issues are just part of life. And even when you pause
I'm
it,
trying to share it
because of the way that things download now, right? It's got like 8 streams going. So when you pause it, it has to like 8 times has to kind of actually pause, and it has to write out everything that it has. So pausing it is a slow process. We'll give it a minute. I know it takes some time to get caught up.
Can you, Professor, can you see my screen?
No, I cannot see your screen yet. Give it a minute. I will give you a thumbs up when I can see it.
That's weird. It says it's sharing.
Yeah, I see a thing that says Catherine has started sharing, but when the network is kind of slow. Oh, when Catherine gets kicked out because of the slow network. All right, you there, Catherine?
Yeah, I'm here.
Okay.
Drop and then it can't.
Yeah, it seems like we're having some problems with you. I think you might not be able to share your screen until that download is done. Yeah. All right. I'm going to be back in 1 minute. I'm going to go get a drink, and then we will get everybody caught up, and then we will start on the actual buffer overflow.
Sounds good. I think I'll do the same.
All right.
I just share my screen, Professor. Can you see it? All right. Good thing I was wearing pants. I'm
All right.
back.
So, Catherine,
I-
how's your connection now?
Can I share my screen now? Yeah,
Yes, please.
yeah, I think the connection is back, but it keeps dropping. I don't know why.
You might have neighbors doing home improvement projects, and every time they run a power drill.
Okay, can you see the screen? Still not seeing?
Not yet. Oh,
Okay,
there we are.
okay. So I have this, I powered off just now.
Mm-hmm.
So should I power it back on?
Powered on. And this is all you're seeing, right?
Yeah,
Yeah, that was doing the same thing to me. Don't worry about it.
Okay.
Let's go to your Kali box
okay.
and then run that scan again.
Is this the right one? I was
Yes, based upon your IP address, that is correct.
Okay.
Okay. Now I don't know why yours is not it's probably you and I have different versions of Nmap. My version of Nmap is automatically doing reverse name lookup,
Oh,
whereas yours is not. So that's why mine has the names, yours is not. But notice that your IP address is 5, and then there's a 1.6, right?
mm,
Now scroll back down to the bottom. Yeah, you're 5. 192.168.1.5. But
Right.
if you scroll down to the bottom, you'll see 192.168.1.6. That seems pretty likely to me to be Brainpan. So go ahead and do Nmap -p
lowercase or uppercase?
lowercase. Yeah, so this is for ports, space, and then do 0-15000. We'll just do the 15,000. It'll be fast.
1500.
3 zeros. One more 0.
Oh.
So you're doing ports 0 to 15,000, and then put in 192.168.1.6.
1.6. Okay.
Run it. Okay, and you see the 2 ports that Brainpan has, Abyss and that sensor management, right? So,
Right.
and by the way, Nmap didn't do anything. It didn't talk to those ports. It just got a response. So it's just guessing as to what's there. So again, let's go ahead and connect to the 9999. So do NC for Netcat. 192.168.1.6. And then 9999. So that's telling Netcat, hey, just talk to this port, see what it sends you. Okay. Go ahead and put anything in here.
Oh,
All right. So let's go ahead and do derb, since Vince was just asking about it. So type in derb, which is, again, it's a directory buster. And then http://192.168.1.6. No, stop. Hit the up arrow. Colon 10,000. So that colon tells it what port to talk to. Now run it. So now it found something, and this is where it finds bin, right?
okay.
So this is where you would go in your browser to, so actually go ahead and highlight that /bin on your thing there and copy it.
Where is
The
it?
HTTP 192.168.1.6 10,000/bin. Highlight it
Oh,
with your mouse. Just select, no, the one beneath that. The one that already has bin there. There you go.
I think you can control click it and it'll just open.
Yeah, that's right. You can control click it.
copy and then go to.
There you go. Okay, so go ahead and download this. No, save it. Save it. Don't open it.
Oh. Okay.
Now you can go to your home.kali, click there. Downloads, and then drag it onto your desktop. You're gonna have to minimize something else.
I have to minimize this.
Or you just drag it to the Windows desktop. To the
Okay.
Windows desktop.
Oh, my window desktop. Oh,
Yeah.
okay.
And this is where I said you have to have that enabled. So
Okay.
And you do. So, okay, so you're good. Okay. That's all you need for right now.
Oh, okay.
All right. Okay. Vince's keyboard battery died. Was it somebody tweeted a couple years ago, you know, I can't charge my book. I can't read because I can't charge my book because my roommate is charging his cigarette. The future is stupid. All right. So right now, let me go ahead and let me share my screen with you guys. And I'm gonna keep sharing just a portion so it kind of fits right. So I have imported my Windows 10 dev, right? And again, I want to go to settings. I want to go to advanced, and I want to make sure that these are turned on. So that way I can drag things on and off the desktop. So before I do this, is there anybody who right now is not at this point? Is there anybody who has not downloaded their Brainpan executable?
I'm just a few minutes away from finishing the second one.
From finishing what?
Finished downloading. What was the WinDev?
Okay, so
AKA.
So you're going to be a little bit behind. That's okay. But
Yeah.
everybody else is squared away, right? Or no? We can get everybody up. Josh, I don't know what raising your hand means. I don't know if you mean you did it or you didn't do it.
I haven't got that far yet.
Okay. So do you have Brainpan running?
Yeah, right now.
Okay. So when have you identified its IP address?
Can I share my screen?
Yes, please do. Let me stop sharing. All right, that's fine. So you're here on Kali. All right, so you got your IP address. All right, you know what? Stop. I think you have the wrong network set up because your IP address is a 10.0.2.15. That's usually NAT. So can we go back to your what do you call it? Your virtual box, the main window, the box at the bottom. No, the virtual box main window. There. Yeah. All right. Click on Kali. And then click on settings. And then go to network, please. Yeah. See, you're on NAT. So what you're going to have to do is you're going to have to shut it down and change it to bridged. Click OK. Start it up. Oh, Josh didn't change his Kelly password. You see him out in the world, you can hack him. All right. Now, I always start by, so do IP address. So you see, now you're a 192.168.254, right? Which is your wireless, you know, that's an IP address from your Wi-Fi card. So that probably is correct. Now try the Nmap-SP and then 192.168.254.1 to 254. By the way, if you highlight it and you do Shift Insert, you don't have to copy it. It'll it'll paste whatever you highlight.
Just this one.
Yeah, the first 3 octets. Or you can just type it out. And then .1, no, because you want to scan the whole network. So .1 dash 254 dash. Yeah. So now you're scanning the whole network to see what's there. And there you see, so Brainpan on yours is .35, right? So now open up your web browser. Since we've already done this, right? Go ahead and open up your web browser. And go to http:// that IP address :10,000 for port 10,000 /bin, actually /bin /bin /. Now, under general, advanced. So you already have it turned on. You can drag it onto your Windows desktop. You're good to go. If you make a little space. Which, by the way, that's a good thing to have turned on anyways for, NCL and stuff like that. You're always moving things back and forth. Perfect. You're exactly where we want you to be. Anybody else? Yeah, I didn't see Jason's chat, but his way of doing it works just as good. Okay, so so now I have that there. Let me go ahead and start up. I imported the OVA for WinDev 2014 eval. It'll start up. Can I make it a little? And again, this works with any Windows virtual machine. I just happened to pick this one because this is one that I saw out there that is being pushed for development and evaluation. You can test stuff. And even though it was a very large file, it was relatively easy because there's no usernames or passwords or anything. You're just in. And I'm just in. So now I can drag Brainpan onto there. Or did I not turn that on? Settings, advanced. No, I did. There we go. I was too fast. So it takes a minute to install the virtual guest editions. So now I have Brainpan here. Now I still want to be able to reach this from my Kali box, which has logged me out. But luckily, I don't have to scan for this because I have access to this machine. So I can do CMD, and I can do IP config, and I can see that, okay, oh, what do we see? NAT address, right? That looks like a NAT address. Yeah, Lazaro, you could probably get this to work on your Windows host machine, but really, it's much easier to have a VM. And that was the large file that I linked to. But this is a NAT address, so let me go ahead and I'm going to shut it down. Power off the machine. Let me go back here. Let me go to settings, network, and change that to bridged. Click OK. Start that bad boy up. Do. And most buffer overflow challenges that I've seen are Windows based. I think just because it's easier, because with Linux, a lot of the patches that stop buffer overflow attacks are at the kernel level. With Windows, even with a Windows 10 machine, it depends on how the application was compiled. So you can take an application, compile it with old or substandard flags, and it will come up weak. The OSCP buffer overflow was Windows, and it will always be Windows. I want to say yes. All right, so now if I do CMD, and I do IP config, we see that my IP address is 192.168.254.110. All right, which is good. So let me go ahead and test out Brainpan. Let's see what happens if I just double click it. I'm going to allow access on everything. And it just says, okay, it's bound port 9999, and it's waiting for connections. Let me go back to Kali, and let me test it, right? Because remember, this was IP address 192.168.254.110, right? So let me go here and let me do netcat 192.168.254.110. Again, port 9999. Adjust that a little bit. And oh, I got Brainpan. It says access denied. If I go back and look at Windows, oh, I got a reply, copied 10 bytes to the buffer, right? The check was -1, which means it wasn't the legit password, and it was just AAAA, right? So I copied 10 bytes to the buffer. Okay. So we now have our own copy of Brainpan running on a virtual machine we control and we can access, right? So this is good. This is exactly where we want to be. Let me go ahead and I'm going to minimize that. I'm going to make this a little bit bigger. Can you guys see this Windows machine okay? Is everything readable for you guys?
Yeah, it seems like it.
Okay. All right. So what I need now is I need a way to see exactly how is this program running if I can get it to error, right? And just to get it to error, what I can do, let me try this. Let me try that. And let me just see what happens if I do a whole bunch of A's. And again, if I get tired of typing, I can highlight it and then just do Shift Insert. And I hit Enter. And what did it not do this time?
Didn't say log on denied.
Yeah, that's right. Didn't say access denied, right? So if I go back to my Windows machine, we see it's just gone. It just crapped out. So I know that I can overload it. I can get it to crap out, which sometimes that's fun. But I want to do something more. I want to get it to run my code. So for that to happen, I have to see how it craps out. For that, I need a debugger, and the debugger we're going to use is, and by the way, it hurts me to use Edge. This hurts me, but I'm not going to make you watch me download Chrome. So we're going to use the Immunity debugger. And I'm going to copy that and paste that there for you guys. And it's free. You click here. They ask you to fill out this stuff. You can put in anything you want. And click download. Okay, and it's coming in down here. It's not a particularly large file. And once I have it, I will never use Edge on this thing again. Do 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 do. All right, so it's downloaded. I'm going to open the file. I'm going to say yes. I'm also going to close Edge here. Oh, cancel. Going to close Edge. There we go. Now it tells me, hey, by the way, you don't have Python installed. Python is necessary for Immunity Debugger. Do I want to automatically install it? I'm going to say yes. I'm going to accept the terms. I'm going to install. Click close. Okay, now it's going to install Python. I'm going to just click next, click next. Do, 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 do. Click finish, and we're done. Now I'm going to start up Brainpan. And it's running like it normally is. So what I want to do is I want to take that debugger and I want to attach it to the running process so that the debugger knows about it and it can see what is actually in memory. So I'm going to start up Immunity Debugger. And then I'm going to go File, Attach. And luckily, I don't have a lot going on this machine. I'm going to attach this to Brainpan. Select it, click Attach. Boom. Now, a couple things I want to point out to you. There's a few different windows here, and Immunity Debugger is the worst if you start playing around with Windows. It hoses up everything, and I haven't figured out how to get around that. But just to be aware, The other thing is, as soon as I attach it, notice in the bottom right-hand corner, it says paused, right? So when I attach the debugger to it, it stops the program where it is, which is good because we want to see what's happening, but I'm going to have to start it again before it's running. So if I was to try to connect to it right now, it's not running, it's paused. This window right here are the instructions, right? So these are the assembly or the actual computer instructions that were being run at the time that it got paused. Over here are the registers, right? So this is what the CPU has in it. The stack pointer, right? The ESI, which is the return value, a bunch of other registers. And then down here, this is the stack in memory. So this looks kind of similar to other memory or hex dumps we've seen in the past. On the left-hand side is the address. Then we have the hex values, and then we have the ASCII interpretation of those hex values, right? So those are our three windows. Does this make sense to everybody? So I have to start it up again because it's paused. So I got to click here on the little play button. Or if I go to debug, I can choose run. So I'm going to choose run. And now it's running. So it is active right now. Let's see if we can crash it. So I'm going to go back to Kali. And I'm going to grab a bunch of that. I'm going to do exactly the same thing. Hit the up arrow. And it asks for a password. I'm going to do shift insert. Then hit enter. And again, it looks like I'm not getting a response. Let's go over to the Windows machine. And what does it say in the bottom right of the Windows machine? Excuse me, the immunity debugger. It says paused. So it's stopped at this point. And then if we look up here at the registers, well, what do you see? So you see a lot of A's, right? Which is what I just sent. And remember I said the ESP is the stack pointer. That's that point that's where we're writing things. If I right click on this, I can follow in dump. And then down here, we can see, okay, these are all the A's that I wrote, right, in there. Now, take a look at that. What else do you notice about the dump? Let's see this. Anything else stand out to you? So we see a bunch of A's. What else do you see there?
Access violation.
41.
It is an access violation because that's not a valid address, right? But what else do you see in the dump in this bottom left-hand window that we're looking at?
There's a lot of 41s.
41. Why is there a bunch? 41 is the ASCII value, exactly. Take a look at the register window in the top right. What do you notice?
I noticed it takes A twice, and then it goes into the module entry point.
What I want you to know, so this ESP is pointing, is an address of a spot in memory where we wrote a bunch of A's. EDX is another address in memory where we wrote a bunch of A's. But the EBP, we overwrote that with A's. And the EIP, we overwrite that with A's. The EIP is the important one because the EIP is the next instruction. It's saying, hey, next time you do something, do this. If I overwrote that, that means that I can tell it, hey, go do this instruction. Go run this. That's a huge deal, right? that means that this is directly vulnerable to a buffer overflow. So that's the thing that you're kind of looking for whenever you do a buffer overflow attack, is can I overwrite this EIP register with some value of mine? Everybody with me? Any questions at this point?
So is
let-
the question now, how many A's do I have to write before I write down login?
That's a great question. Let's go ahead. So I'm going to stop this right here. And then I'm going to start it up again. If I go to File, now it's there, so I can just click on that. And it starts it up again. But every time I start it, it's still paused. So I got to hit that run, hit the little arrow there. So now it's running. And then I'm going to put that away for a second. I'm going to go back to Kali. Okay. So what I want to do now is I want to fuzz it. And I'm going to give you guys a file. Why is it not working? So let me go ahead and, where is it? There we are. All right, so I just gave you guys a copy of my proof of concept file. So, and this is a very common, this proof of concept that I'm giving you, it's all over the internet. This is what everybody uses to start fuzzing. And what we're going to do is we're going to build this from fuzzing into an actual exploit. That's our process. So I'm going to open it up in Vim. And I'm going, so this is a Python file. And it takes as an argument, so right up here is your code, right? User bin Python. It imports the socket library, then it imports the system library. The only argument it takes is the size of whatever, this is the size of the buffer that we're going to send to our target. Then it tells you what size it is. And then this is inside a try, not a loop, block, just because you're doing network stuff, so things can time out, right? And then it says I'm sending evil buffer. This just says I create a buffer of all capital A's at whatever size we specified on the command line. Then my buffer starts with nothing, and then I add input buffer. The reason the buffer, you always start it with nothing or with a blank one and then add the input buffer, is it's very common for these buffer overflow attacks for it to require something first. So, you might need to send the word hello and then wait. You might, you might need to send, some code. So that's what that spot is. This one is very simple. So it starts with nothing, and we can just send it all A's. This line creates a socket, right, called S. Then we connect that socket to our IP address. Now, my IP address was 111, right? I think it was. Let me do. Oh, that's weird.
Don't you need the IP address of the Windows machine?
Yeah. So, no, it's 110. Oh, it's 111.
It's probably not still running, right?
Yeah, no, my Windows machine is 110. 111 was my Brainpan. That's right. So it is 110. And I really hate Z shell, but I haven't fix it on this machine to go back to bash. All right, so 111 is my, and I totally just forgot again. 110. 110 is my Windows machine. So it was right the first time. So this is going to connect to this IP address and this port. And then it's going to send whatever my evil buffer is. Then it's going to close and then it's going to print out done. So Lazaro said, are we trying to figure out the size before it crashes? Exactly. Right? And we're going to do this in stages. The first stage is just how many do we have to send to get it to crash? Then we're going to try to figure out, all right, exactly where does it crash? And then we're going to figure out how many can we send afterwards. So those are the stages to figuring out the crash. So right now, all we're doing is sending in a number and seeing if it crashes. So that's good. I'm going to save that. And I'm going to do Python, Brainpan, and then I'm going to give it a size of 10. And it sent an evil buffer of 10. If I check my Windows machine, see how it still says running down here? Right? So 10 does not crash it. Let me go back to Kali. All right, what if I send it 100? So 100 does not crash it. What if why did that not show up? Well, what if I send it 1,000? Okay. See how it's paused? See how it says the stack, the EIP is 41, 41, 41? So 1,000 crashes it. All right, so let me go ahead and I'm going to go over here and click on debug. I'm going to, I never restarted. I always close and then start again. I don't know why. Force a habit. But remember, every time you restart it, it comes in paused. I have to click a little arrow to run it. So somewhere between 100 and 1,000. Let's try 500. It's still running. What should I try next?
750.
750. We're dividing it into half each time. So 750. So 750 crashes it. So I know it's somewhere between 500 and 750. I'm okay with that, right? I'm going to stop here. So Nolan said 2,000. I can try that. Here's the thing, Nolan. You don't always want a bigger number, because sometimes the way, it's not just that you crash it, it's the way you crash it. Now, I know I'm okay because I'm overwriting the EIP with 41, 40, with all A's. So I know that that register I really need to be able to change, I can hit that one. If I try 2,000, 10,000, 100,000, that might not work. I might be putting different values into there that I can't control. So we want to find the smallest one, or we want to get close. So 750 is close enough that I can find the exact number from here, right? So fuzzing is we call it fuzzing because we're fuzzing the values, right? We're trying different values of approximately the same one. So I'm going to go ahead and stop it and start it again. I'm going to start using restart. I probably should. Don't forget to run it so it's not paused. So now it's running. So this is kind of what I want everybody to get to right now, right? Is everybody able to use this proof of concept, crash Brainpan, such that you can see that the EIP is overwritten? That's our goal. So who's there right now? Who's got that working? Zaro's good. Jason's good. Who needs help? Who needs help but won't ask for help? Is that it? Do we want to just move on? All right. So let me check. All right. So what I want now is I want to overwrite the EIP with a unique code. And that unique code will tell me exactly how many bytes in is EIP, right? So that's the next thing. I want to figure out. So I know it's around 750. I know it's more than 500. I know it's less than 750. It's in that range. So I want to write that in, right? So what I'm going to do is I'm going to make a copy of my proof of concept, if I can. So I'm going to copy that, and I'm going to make this brainpan underscore pattern.py. Then I'm going to create a pattern using a tool called Msf. I think it's dash. Yeah. So I'm going to run this tool msf-pattern underscore create. And let's see what the options are. The only option we really need is length, right? So I'm going to do dash L. And how long does it have to be? 750. There we go. I know it's going to be within 750 bytes. So I have this pattern that I can use to uniquely identify how many bytes in until I hit that EIP register. So I'm going to right click on it. I'm going to copy that. I'm going to vim brainpan underscore pattern. And now I'm going to create a variable at the top. I'm going to call it pattern, and I'm going to set it equal to. I'm going to paste it in there. So now I just have a variable with that pattern, and then down here, instead of the buffer adding the input buffer, I'm going to add the pattern. And actually, I don't need the size anymore either. So I'm just going to comment that out. I'm going to comment that out. Sending evil buffer. Okay, so this should work. Let me go ahead and Python pattern. And by the way, every time I do this, I stop right before I run it, and I go back to my Windows machine and make sure I have my debugger running. Because otherwise you just have to stop. You have to go back and do it again. And I've done that. I've done it enough times that I always go back and check. So it is running. So I'm going to try it. Oh, at some point it prints size. Oh, there we go. So let me comment that out. Now let's try it. Sent the evil buffer. It says it was done. Let me check my Windows machine. Okay. So it's all crashed, but notice it's got, if I look here at the, if I follow the stack pointer in dump, it's got that weird pattern, which I sent it, which is correct. What I'm really interested in, though, is this EIP, because remember, that's the important register. So let me right click on that. Let me copy the selection to the clipboard. And then let me go over here, and I'm just going to echo it so I have it here. So now I want to find out where in the pattern that is, and I do that with Msf -pattern offset. And again, we do -H to see the options, and we just give it a query and a length, and it should find it. So we'll do -length, and our length is 750, and our query is that. And it says exact pattern match at offset 524. So this means that after 524 bytes, after 524 A's, the next 4 A's are what's being written over this. So if I'm going to make it go somewhere else, that's the one I need to hit. Does this make sense to everybody?
You found the number by looking in the ESP or the ISP, and then you just
EIP.
so you look at the EIP hex, and then you saw the range and the numbers.
I right click on EIP and I copy selection to clipboard. So
Okay.
So this is not the actual. Is that the ASCII value? No, this is the numeric value, not the ASCII value. Right? And it can be different ways in different machines that you're attacking. That is it. But the key thing to understand, it's always going to be some number less than what crashes it. And you will always be able to find it with the ASCII pattern offset. And then after you find it, then you test it. So that's the next thing we're going to do is we're going to test it. But I want to make sure that everybody's here before we test it to verify exactly where it is.
You said numeric value, so is it literally the number, or because like I'm thinking of like hash,
So-
octal, but numeric.
These are hex values. There's
Okay.
4 hex values there,
Okay.
right? Yeah, those are 4 hex. So what I input was ASCII characters, but what I get out is what it shows in the register is the hex.
So are you then gonna like convert that hex number into ASCII, and then that's where you find out?
I don't need to. I already put that query in here, and it told me it's at 524.
Oh, so that's where it that's the number of words you need until it crashes.
Yes.
Okay.
Yes. Number of bytes. Exactly.
So then the hash you need the assembly to read is the last, like, what? The last couple of numbers on 524.
It's not till it crashes. It's till it writes over that pointer.
Okay. So 524 is where EIP, I'm sorry if I get it wrong again. That's where it was written.
So the data, after 524 bytes, the next 4 bytes I send it are what overwrites EIP.
Okay.
So I can control what EIP has in it, and EIP is the address of the next instruction.
Yes.
So I'm going to use that to tell it to go where I want it to go, to my code.
So that you just type in until 524, not 524 letters, like until you get the.
Yeah, 524 bytes.
Mhm.
And like I said, we have a couple more steps before we actually start getting it to run code. But this is the first part, is just figuring out where does it, what is the actual spot where it gets written, where it writes over the EIP, the instruction pointer. Does that make sense, Nolan?
Yeah. Just
Any other
cut off
questions?
line and then go to the next thing, next instruction.
Now, does anybody else have is there anybody else having trouble getting to this point? You can share your screen and we can help you out.
I just wanted to understand the concept again. So that 35, 72, 41, 34. So that's the hex pattern, right? Like 35 is 5, the number 5. Then 72 is the letter R. So that's in the pattern that you generated, right?
Yeah.
Like we can, like, right? Is it in there? It's somewhere in there, right? The 5R, something like that, right?
Yeah, it's gonna be somewhere in there. So it'll be 524 bytes. So which should be, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 lines. So each line's going to be 75, right? So 75, 150, 300, 450. So 450 plus 7. So it should be actually.
Yeah, so let's say that it's somewhere here, or let's just say. You're going to replace that eventually with a command?
Yeah.
Or
actually,
or something.
Vint, it's going to be right here. Yeah. Because it is little endian, so the order gets flipped, right? We don't really need to worry about that because we're going to take that into account later on.
Yeah, I got you. Yeah, so it's little endian, so it's flipped. So that's why it's this 5R. Okay, because I was looking for like 5R, not R5.
Yeah.
But that's what I by replacing the so it gives an EIP, right, which is at 35, 72, whatever, and then which is the instruction pointer, and then you're going to replace that memory pointer, right, where it points to. You're going to replace the command at that pointer.
Yes. So I'm going to overwrite that with an address of a different command I want it to run.
Of an address.
Yeah.
Okay. All right. Okay.
And we're going to find that address later on. And by the way, if this seems like a lot, it is. Luckily, TryHackMe has a really good buffer overflow room. So if you want to practice this, you can practice it in there. Hack the Box has a buffer overflow. And also Brainpan is actually a series of Vulnhub machines. So there's like 6 of them. So you can keep practicing this if this is something you're interested in. So it's a lot. You don't have to get it all right now, right? Okay, so once I know that the offset is 524, I want to verify that. And what I do is I'm going to copy Brainpan proof of concept to Brainpan. I'm going to call it spacing. Well, we'll call it buffers.py. And then I'm going to vim Brainpan underscore buffers.py. So this is our original one where it took 1 argument of size. I'm going to change this and I'm going to make this a size. And then, let me do 2yy. I'm going to take a second argument and I'm going to make that C size. Go over here, replace that with a capital C. So this one's going to take 2 arguments. It's going to take the size of the A's and the size of the C's. And actually, let me go ahead and change my print statements to reflect that. So now I'm going to send it A's, B's, and C's. So I'm going to say input buffer is I'm going to get rid of the input buffer here. And we're just going to build out everything in buffer. So I'm going to say buffer is A times A size. Then the buffer, we're going to add to it B times 4. And then we're going to add to it C times C size. So this is the same as our proof of concept, but our proof of concept before just sent all A's, however many we told it. Now we're going to tell it, send this many A's, and how many A's are we going to send it?
524.
524. Then we're going to send it 4 B's, and then we're going to send it some number of C's. And what we're really trying to do is figure out how much space do we have to play with before and after the pointer. Because if we have a lot of space, our life is a lot easier. If we don't, we can do some stuff, but we'll have to deal with that problem, right? Yeah. So I'm going to, and here's what I'm going to do. I'm going to do that. So I'm going to leave this up there, and then down here, I'm going to run it Python Brainpan buffers, and then 524 before, and then let's try 1,000 afterwards, right? What do I do before I run it?
Check this.
Turn on the debugger.
Yes, make sure. See, my debugger's not running, right? It's paused. If I had run it, I would have wasted a click. Let me try restarting it now. Let's see if that works. Okay, so it does work. Then I'll restart it. Then I'll click run. It is now running. Now I'll go to my Kali machine. And I'm going to check my buffers. It sent the evil buffer. So if I go back over here, we see it's paused. So we see that the EDX, right, that is pointing to a bunch of A's. The EBP is written over a bunch of A's. What do we notice about the EIP?
It's too small for me to read it, but
Oh, can you guys not read that? I don't know.
You see the Brainpan .311715000. Is that what you're looking at?
Yes. So, but that's not what we expected. What did we expect to see on EIP? We expected to see the B's that we sent, right? So if A is 41, then B should be 42. So that should be 42, 42, 42, 42. It's not. So something got hosed up. And I can check it out here. I can follow in dump. And we see our A's, A's, A's. And then you see a bunch of garbage. And then you see a bunch more A's, and then you see some other stuff. And then we run out of space. So remember earlier, Nolan, when you said, 2000, and I said that can mess things up? It seems like that's too many C's, right? So my buffer after is not that big. So let me go ahead and restart it again. Yes. And run it. So let me go ahead and try it, and let's send it 524, and then let's send it 100 C's afterwards. Let's see what it does then. Oh, this is interesting. It's still not. Still not doing what I expect. Did I copy the wrong thing? No, it's not.
Is that it?
So either something's wrong in my code, which is possible, or so let me go back here. Oop, wrong thing. Let me go back to my Kali. So let me go up here. And well, this is interesting. Now I look at it. So up here, it should print A size is this, and C size is the C size. But here it's not printing that. So it's the right one, Brainpan buffers. Yeah, see, that's what I was thinking. Well, this is weird. So let me try. Oop.
Maybe you forgot to save it.
I know I saved it. But maybe I didn't. Maybe, you know, maybe I just thought I saved it. All right, so we'll do this again. 2YY, and then so we will have A size and C size, and then this will be based upon the second argument. That will be A, that will be C, and I will print that out. And then this will be, again, I was going to get rid of the input buffer and just make it the buffer plus equal A times A size, buffer plus equal B times 4, and then buffer plus equal C times C size. So that was written out. So it says right there, written. So let's try this again. And now if I go over to my Windows machine. Okay. So now this kind of looks like what I expected to see, right? So we see somewhere on the stack a big stack of A's, somewhere on the stack is a big stack of C's, and then our EIP says 42, 42, 42, which is B, which means I'm overwriting it. So everything is right with the world, and I have at least 100 bytes after I write that out, because if I look here, I sent it 100 bytes and it worked. So now the next thing I want to do, I want to say, can I get more than 100 bytes in there? Right? Because the more space I have afterwards, the more space I have to work with, the better. So I'm going to debug. I'm going to restart it. All right. It's running. Let me go back to Kali. And let me try 1,000 now. Let's see if 1,000 does work. So Jason, it's not that you need more shellcode. It's that I need a certain amount of shellcode. And if I don't have it, I got to find ways to make it fit in other places. So yeah, the more space I have, the easier it is. I just have to do less things to make it work. All right, so I sent it 1,000 C's, and we can see, okay, it still overwrote EIP with all B's, right? 42, 42, 42. And then if I follow ESP, which is our stack pointer, we can see that giant stack of C's there, right? And you can see, you might need to get really close to the screen, but you can see where it goes from A, then our 4 B's, and then C's. And I'm getting 1,000 C's there. It might not quite be 1,000. I'd have to do the math, but it seems like I have plenty of space. So I have verified that I put in 524 bytes of filler. I put in the instruction I want to run, and then I have 1,000 bytes for approximately 1,000 bytes to put shellcode, which is directly pointed to by this ESP. So what I want to do is I want to put an address here that will jump to that location. And that's going to be not the next step, 2 steps from now. The next thing we need to do is we need to figure out what are called bad characters. But I have to use the bathroom. So let's go ahead and take a 5-minute break. All right, 5 minutes. And then we'll come back here and we will talk about bad characters, which is the next step of it can be tough. All right, so 5 minutes. All right. I didn't want to punish you guys with my chewing. We ready to go? Been 5 minutes, right? So the question was, why do we need to identify bad characters? And I think the best example of this is, let me go ahead and take a look at what? How did this get so long? All right. It's a nightmare to get anything to fit in this stupid little window. There we are. So the perfect example is HTML encoding. So, for example, in a URL, right? You can't have certain characters, right? You can't have a space character. The space gets converted to %20. In the HTTP format, space is a special character. It's reserved. If I'm sending this over a network, right? If I have shellcode and I'm exploiting a web server, and there's a space in there, it's going to interpret that as a special character and stop. It won't copy anymore. If it stops copying, then it won't. What do you call it? It won't actually overwrite what I needed to overwrite. You know, if I have a $sign in there, or not even a $sign, but if I have, where's the dollars? I picked the wrong one. $sign's going to be hard to find. Is it a pound sign or a dollar? I think it's a $sign. So if I have the hexadecimal value 24, if that just happens to pop up in my shellcode, then when it reads that, it's going to say, oh, this is a special character. It's going to stop copying it, and it will not pass it on to the vulnerable application, right? So bad characters are any character that is identified by the web protocol as having a special meaning, and it'll stop at that point and process it instead of copying over all 1,000, 2,000, however many bytes. Does that answer your question, Lazaro? Okay. So we need to identify the bad characters. And I'm going to copy pasta that to you guys. So that's basically what you always start with bad characters is that list. So let me go to my Linux box. That's the wrong thing. My Kali, and it logged me out again. So I'm going to make another one, and I'm going to copy up here. I'm going to leave. Yeah, I'm going to leave buffers, and then I'm going to copy Brainpan buffers into Brainpan badcar.py. And then up here, I'm going to edit that. Oh, it is, but it is to FF. Apparently, it didn't all copy over. So that last line where it has just /x, it's supposed to be this. That's the actual ending. Thanks. Thanks, Vince. Good looking out. Okay. So I'm going to open that up. Now I'm actually going to get rid of the arguments. We don't need any more arguments. Actually, no, let me undo that. A size is always going to be 524. So we know that we always need 524. C size doesn't matter anymore. So we're going to get rid of everything with C size. And then up here, I'm going to copy this whole thing over. And I'm just going to paste that in there. Move that down a little bit. So what I do is, as I find characters are bad, I take them out of the bad characters variable and I put them up in that comment at the top. And yes, so you always count 00 as a bad character, because I've never, you just always take it out. 00 is always going to be a bad character. So we start with, 1, 2, 3, 4, all the way up to FF, right? By the way, this is a way of declaring a string it's really a byte array in Python. They do not, because it's 1 byte array. So this is legit, right? Just as it is. All right, so just like before, so I have this big byte array of characters I want to test. The A size is still 524. Then down here, when I create my buffer, I create 524 A's, my 4 B's, and then I'm going to add the bad chars. Oh, I think I capitalized it. So I add that to the end. I know this will still cause an error. Sometimes I might need to add more C's afterwards, because it might not work unless you have a minimum number of C's. But I know that this one works with 100, so it'll be fine. And yeah, so now I'm going to send, that's going to be what I send it. 524 A's, 4 B's, and then that big list of bad characters, which is every ASCII character. Let me go ahead and save it. And then verify that it's running on my Windows machine. It's not running. So let me restart it. And boop, 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 boop. Click the play arrow. Go back to Kali. Go back to the bottom. Let me go ahead and run it. Python, Brainpan, bad char. Okay, so is the EIP 4 bytes? That's an interesting question. And it does have to do with, it does get more complicated when you get into 64-bit machines. It's also more complicated because we're using Intel chips with their addressing scheme. It's actually much simpler if you're dealing with something like a Spark, but it's always going to be Intel. So for everything that we do, it's always going to be 4 bytes. But it could get more complicated in other scenarios. All right, let me run bad char. It's done. Just grumbled at me. So if I look over here in my Windows machine, we see that I got my A's. My EIP is all B's like I expect. Let me go take a look at my stack pointer. Follow and dump. And I'm going to change my window size. Can you guys read that better?
Yes, much better.
Okay, because it's really, now it's really vital that we see exactly what's in here. So what's the first value on the stack? Zero, 1, right? 0, 2, 0, 3, 0, 4, 0, 5. Exactly. Those are the characters I just sent, right? And if I was to go up a little bit, I should see, yeah, here's my A, and then my 4 Bs, right? And then it goes immediately into my bad characters. So it's actually not that hard to find my bad characters. I just need to start counting and see, are there any that are missing, or is there a point where it cuts off? If it cuts off, that means that's a bad character, and I can't send that, or it stops copying things over. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and then 1, 0, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F, 20. Let's see, does it go all the way down here? Okay. It does look like there are no bad characters. Now, I will say so 99% of the time, if there's a bad character, it just cuts off at that point, right? That is, so if like D4 is a bad character, it just stops at D4, and then I'll see a bunch of garbage afterwards. But every once in a while, there'll be a bad character that gets dropped, which is still a bad character, but it won't be as easy to find. So it is a good idea to actually go one by one, just to be sure. 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 2, 9, 2, A, B, C, D, E, F, 3, 0 through 3, 9, 3, A, B, C, D, E, F, 4, 0. Okay. 5, 0, 5, 1. And you can also kind of check, because these values they're ending in 0 and 8, right? That's the pattern. If one got dropped, you would miss that pattern. So it does look like we have no bad characters, right? Which is great. That was a very easy one. It's not always that easy, but this was a very easy one. What I'll tell you though, the thing that makes bad characters a real pain is if you don't have enough space under C's for all your characters at once. So if I could only have like 12 C's at a time, that means I can only check 12 bad characters at a time, and I have to send the next 12, the next 12, the next 12. That's what makes bad characters really, really annoying, is if you have a small C buffer. If you have a big C buffer, it's not too bad. Unless you have a ton of bad characters, which sometimes it'll be like, if there's 15 bad characters, like 15 times you got to go through and find and resend it again. Boom, boom, boom. All right, let me go ahead and make that big again. And then let me restart this. All right. So let me kind of share with you where we're at. Let's kind of talk about steps. So step 1 is get the app that you're going to be testing, right? Once you have the app, put it in the debugger and fuzz. And fuzzing means trying input of various sizes to get an idea of about where it crashes such that you can control that EIP. Once you've kind of figured that out, then use Msf pattern create and Msf pattern offset to verify EIP offset, right? So then you figure out exactly how many bytes before I overwrite the EIP. And then you verify buffers, right? The A buffer before the EIP and then the C buffer afterwards. Then we check bad characters, right? Those are the steps so far. So does this make sense to everybody? Any questions on those steps? So we're in the home stretch. So now I got 2 more steps. One, I have to generate and insert shellcode, right? So I have to generate code that will do a reverse shell to me, right? Or whatever else I want it to do. You know, maybe I just want it to you know, to run a command or whatever I want to do. I have to generate the code that does that. And then I have to get EIP to execute that shellcode. So those are the 2 things I have to do. Luckily, I have plenty of space. I have 524 bytes before. I have 1,000 bytes afterwards. I have plenty of space for my shellcode. So this is easy. If I don't, then I got to start doing like funky math. I got to figure out instructions to like add certain values, and it becomes crazy trying to figure out ways to get to my shellcode. So this is going to be relatively easy. So first, let's go ahead and generate our shellcode. And pretty typically, we're going to make our shellcode. Let me go ahead and quit that. We're going to make our shellcode with something like this, and I'm gonna send it to you guys. You also might have some other options that you would set. So these other options, after testing it out, you might need to do these. So the exit function equals thread. What that does is it causes your shellcode to create a new thread and jump to it. That way, if something crashes, or if you crash the actual application, you still have a connection, right? I don't think we need that for this one, but sometimes you need that. Does anybody know what this option? Oh, does anybody know what this option does? I'll come back to your question, Vince. The one, I guess you can't see what I have highlighted. The -E option. That's the encoding, right? And shikata ga nai, you can give it like different iterations. So you can iterate it 1 time, 10 times. But what's really interesting about that is if you use that encoder and do over 6 iterations, your shellcode is unrecognizable by antivirus. Still, like right now today. So if you're dealing with a system that has antivirus, you want to use the encoder to hide your shellcode. Now, it still might pick it up based upon behavior, right? Because antivirus does that. But you know how antivirus identifies patterns, and it says, you know what, this looks like a virus. If you encode it more than 6 times, it can't. So that's a really useful thing in some situations. We don't need it here, but I just want you to know those options. Mostly, we're going to be doing the first Msf Venom option. So let me show you. We're going to start with. So Msf Venom, for those of you that don't know, is a tool for generating. Yes, it obfuscates the payload. Oh, wait, you know what? Stop. Let me go back to Vince's question. I forgot Vince. So Vince asked about the Msf pattern create and pattern offset. Luckily, Vince, both of those take the -H option, which is very helpful. Pattern create, you just tell it a length and how long you want it to be. That's -L. For offset, it's -length and how long it was, and then -Q for query, and then whatever it is you found, right? So they're very simple, and the -H tells you everything you need to know. All right, so going back to Msf Venom. So Msf Venom builds payloads for you. So rather than you having to write your own code or get somebody else's code and compile it, this does it for you. And we're setting our payload to Windows shell reverse TCP. That's a very important, there's a very important thing here. It's shell _ reverse TCP. If you instead have shell / reverse TCP, it won't work. Anybody know why? Any Metasploit gurus? So
Because Windows dashes in the opposite.
no, because none of this is on Windows yet. This is still on my Kali machine. So the / is a 2-stage shell, which is it has a smaller shell that it uploads, and then it will download the rest of the shell from your machine. So that only works with Meterpreter, right? That only works if you have the Meterpreter in there. If you want a 1-stage where all of the code is in one thing, you have to do the _. And I only point that out to you because I know at some point you're going to be Googling these commands and you're going to see this. And it's not going to work if you just set up a listener. So if down here, if I just have like netcat -listen verbose np 4444, right? That's a dumb listener. That will not work with this payload. It'll only work with this payload. So that's why I point out the difference. So I specify the payload and then the local host, which is my IP address, which is 192.168.106 for me. Yours will be different. I'll insert that in there. The local port, which I do 4444 out of habit. So a little bit on port choice. It's easier if you do a port over 1,000 because then you don't need to listen as root. However, if you're trying to hide it, or if you think that there's like a firewall or something, you can do port 80 or port 443, which are the HTTP and HTTPS ports. If in doubt, use one of those. As a matter of fact, I am going to use one of those ports. I'm going to use 443 because that will work everywhere. Nobody blocks 443 because of all of the HTTPS traffic that has to go through. And then -B for bad characters. And my hexadecimal of my bad character. Now, the only bad character I had was 00. And then -F for format. and my format is going to be Python. So if I do it like this, it's going to give it to me in a Python like array. And I do that, and it's going to spit it out to the screen. Okay. So I can plug this right into my Python code. So I'm going to copy that. And then, I'm going to make another copy. Let me do copy Brainpan. I'm going to copy bad characters, and I'm going to copy that to Brainpan final PLC. So here I'm going to copy that in. So I now have a buffer variable that has my shellcode in it. I'm going to delete that. I don't need the bad characters anymore. My A size, my A size doesn't change, right? But instead of adding the bad characters, I'm going to add the buffer. Now, this works because, actually, no, I'm going to do, buffer plus equal buff. All right, so two different questions here, right? So Vince's question, does this work even if the C buffer is small, like in your earlier example? No. If it was smaller, I wouldn't be able to fit all this code in there. So I'd have to put it here, right? And then I'd have to do something else to get it to jump there, which would be complicated, right? So I'd have to set up some instructions that do some math, somehow load an address. We're not going to deal with any of that. Luckily, we're just and let me show you guys. So let me throw bad character out again, right? So I just ran that again. Let's go back and take a look at our Windows machine, and we can see, right? We can see our overwritten instruction pointer. If I right click on ESP, right? That's the ESP, the stack pointer. If I right click on that and I do follow and dump, I see the bad characters right there, right? So I see 0, 1, 2, 3, 4. So exactly what I wrote in order. I wrote 524 A's, 4 B's, and then the bad characters, and I'm pointing right at it with my stack pointer, right? That means I can jump right there and do what I need to do. Otherwise, I might have to find out the address of something. So like this one right here, the EDX. I might have to jump to that instruction, or I might have to do some math and say, okay, add 5,000 to EDX and then jump to EDX, right? So it gets much more complicated, and then you start getting into how to do, assembly level instructions and things. We're very lucky we don't need to mess around with that, and most of your buffer overflows you really don't. Most of your buffer overflows are exactly this pattern, because this is complicated enough. Does that answer your question, Vince? Okay. let me restart it. And then, let me run it. To go back to Jason's question, right? Is this a Nmap? So the ASCII character with a hexadecimal value of 90 is a Nmap, or a no operation. Means do nothing. It tells the CPU don't do anything. So I am putting 16 Nmaps there at the top of my stack. And I do that to give myself a little bit of a buffer, because I have no idea what the hell this code actually does. I don't know. Somebody else wrote it. Sometimes that it'll actually kind of like copy some values up and down in order to like decompress itself, or if I use that encoder, right? So it might need a few extra spaces to copy data. So by using that Nmap, I give myself a little bit of a buffer. So 524 A's, 4 B's, 16 bytes of nothing, just it skips right past them. We call it a Nmap sled because you slide right into your code, and then the actual code I want to execute. So when I run this, so actually, let me go ahead and run this now. So if I do Python Brainpan final, and then I go back to my Windows machine. We see that EIP is stopped. If I look at the stack pointer, if I right click and follow and dump, you can see my 90s there, and then you can see my code, DA, DF, whatever. And if I look at that, yeah, DA, DF, D9, right? So it's going to go, the stack pointer points at my Nmap's. It's going to say, okay, no operation, no operation, no operation, 16 times, and then it will start executing my code, whatever that is, right? I don't know exactly what it does, except that it should call back to my machine. Everybody with me? Any questions at this point? Okay. So now here's the rub. How do I make it start executing from that stack pointer, right? How do I make it start doing that instead of just kind of going through, instead of crashing, right? So what I need to do is I need to find an instruction that will execute things from the stack pointer. And the instruction is called jump ESP, right? If you remember, there was an E in front of the stack pointer, ESP. So that's the actual instruction, jump ESP. And I can find out what the code is for that by running the Msf NASM shell. Wait, no, that's the wrong thing. So the Msf NASM shell takes me to this, and then from here I put in jump ESP, and it will tell me, okay, the opcode for this is FFE4, right? So somewhere I want to be able to search the program, the target program, and say, can I find somewhere where it has the FFE4? And then I can put that instruction address into EIP instead of B, and then it will jump, right? So let me kind of show you guys, let me draw it out for you to make it a little bit more clear. All right. So right now, let me do, oh, I don't want I want black. So I've got this great big line of instructions, right? So right now down here, I have the, or let's see, over here, I have the ESP, right? The ESP has some number in it, and that number is going to change every time. 0x, 40005. Let's say that's what it is. Then over here is address 0x 40005, right? So there's a connection between those two. And then here I have my Nmap, however many times, and then my shellcode, right? So I have a register that points to it. And then here I have the EIP, which currently has 42, 42, 42, 42, right? Right now it has a garbage value that has no meaning. Somewhere in this code, somewhere, there is an instruction called jump. Ooh, I'm gonna do that so you can read it better. Jump to the ESP, right? And that's at, let's say that's it. What I need to do is change this to say 0x10003. This instruction will get loaded into the CPU. That's what actually gets done. And when that happens, it will jump to this point. It'll start executing my code, and I should get a shell. Does that make sense to everybody? Yes, no?
So, so essentially the code, there's probably in the code many times where it jumps to the stack pointer. So we're going to look for an instruction that says that, and then we're going to overwrite the instruction pointer to go to the address where it executes jump ESP, because it doesn't really care which jump ESP it is. It's just that every time that it jumps ESP, it's going to jump to the current stack pointer. And if our stack pointer is overwritten with what, or if the address that the stack pointer is overwritten with it, so it's going to jump to our spot if we execute that instruction.
Exactly. Yes. And if we, if our code was somewhere else, we wouldn't use the stack pointer, right? And there are much more complicated examples of this where people put their own addresses in. The thing is, when you're crashing systems, you don't always know where things are in memory, so you can't hard code it in. I can't put the value 4005 in there because I don't know that 4005 will always be the number, right? So I have to find the instruction and then hard code that instruction address in, because that instruction address probably will not change, because that's in. And some of you guys, we talked about this before. Wrong thing. There's different sections of memory, right? So the jump ESP is here in text. That doesn't change. Our stuff is here on the stack, which grows and shrinks. So that can be at different values depending upon, every time you run it. But jump ESP will always be in the same place, right? And there are other commands you could use, in more advanced ones. But in your basic buffer overflow, which is, again, what you encounter almost all the time, it'll just be jump ESP. So now I know that the encoding for jump ESP is FEE4. And if I go to my Windows machine, I can run, are they called shell commands? I think they're called shell commands using this thing called Mona. And I'm going to just, oh wait, I can look at what is running right now with Mona modules. Oh, all right, let me, wrong thing. All right, so I have to install Mona. I forgot about that. Let me go. Gotta use Edge again. Okay, so yeah, Mona.py is what I want. So I'm going to click on that. Then I'm going to click on raw. And I'll go ahead and copy pasta that to you guys. And then I'm going to do save as. And I think I put it in C Python 2.7. Let me try it here. All right, let me try this again. Okay, so it says here inside the py command, inside the immunity debugger application folder. There we go. Save as. Immunity debugger, py commands. What? Communism. Let me stop it and see if it'll let me then do it then. So I don't know how I don't have permission to copy it. Let me try this. Wait, no, let me try CMD. What's that?
Oh, nothing. You're doing it right now. Where the hell is that user file? Open file location.
Oh, so it's just the user file. All right. All right. Okay, so copy. So copy that to
I think there was an immunity debugger folder.
there, you're correct. Okay. So I should be able to. So that's the command I had to use to copy it over on this particular. That's kind of annoying, actually. So now, if I start up the immunity debugger, and now if I start up my Brainpan, if I do Mona modules, there we go. And of course, this is unreadable. So let me shrink that down a little bit. Can you guys read that now?
It's much better, yeah.
I can make it even bigger if I make that over. So so what Mona modules does is this is a plugin for the immunity debugger that is basically showing us, okay, here are the modules that I currently have access to. Here's what I can look into, and I can check to see information about them. In particular, Rebase, Safe SEH, ASLR, NX Compat, and OS DLL. And what you want is for those to be false. So those are all ways that modern applications make it so that you can't hard code in that IP address, or should be that instruction address. So rebase will change the base where the math starts. Safe SEH will change the error handling, right? ALSR will randomize where certain things go in memory. All of those things make it so that what the technique we're doing would not work. And if you do this on any modern program, you'll see that those will all be enabled, right? But now we see that they're not enabled, they're all false. So this technique will work. And what I'm looking for here is the module that I'm interested in. And the module I'm interested in is brainpan.exe. Sometimes there might be supporting DLLs, and you can also use those, right? You can jump into DLLs, which is a pretty common thing for buffer overflow exploits. You know, there's some library that somebody put out there and they haven't updated in 5 years because they don't work on it anymore. This other guy used it as, you know, as part of his code, and then the library is vulnerable. So all of a sudden, you know, you can execute buffer overflow attacks against the actual application. So once we know the module we're interested in, we're going to attack it, and we're going to, oh, did I put this command? Let me copy. So that's the command, right, to see what modules are loaded. And then in order to look for the jump ESP command, so this is saying in Mona, use the find option, and I'm searching for This is at FFE4. Remember, that's what we got earlier with the NASM shell. And I want you to search in brainpan.exe, right? That's what this command does. And it found a total of 1 pointer, right? Because this is an easy one. On a hard one, it might find multiple pointers, and you have to kind of play around and figure out which one works. Another important point is you have to look at that address. What cannot be in the, so the address here is this, right? The 311712F3. What cannot be in the address and have and me send it over that we've talked about?
The FF?
No. Bad characters. So if the address happens to contain one of your bad characters, you can't use that one. I'm going to right click on that and copy the address to the clipboard. And then I'm going to make that big again. Let me stop that. Let me just let that run. So now I get the running machine. What I might also do is I can, at this point, put a breakpoint at that address. So I can go to that address and put a breakpoint. Yes, Vince, we can use that address because there are no bad characters. Yeah, so I could put a breakpoint at that point and make sure that it's going where I intend for it to go. I'm not going to do that because I know, where we're going. So let me go ahead and go back to Kali. And let me quit this. So that's my address, just so I have it there. So that is what's going to go here in our B, or instead of B, we're going to have this. One /x 17 /x 12 /x F3. Yes, exactly. I was waiting for that. So this is the address as we as human beings would read it. 311712F3. But our machine is little endian, right? So that has to be reversed, which is why I always write the actual address as a comment there, in case there's in case I mess something up, so I can refer back to the original address. So it's actually going to be F3 121731. Now, why is little endian reversed? It just is. That's just kind of the way that it works. It's just a very common thing for. It just depends upon the processor. So some processors are little endian, some processors are not. I think all Intel processors are little endian. So it'll always be little endian when you do these types of challenges. All right, so I'm going to save that. And then up here, I'm going to go ahead and I'm going to split that one. And I'm going to start a listener on port 443. If you recall, port 443 was the one from our original Msf Venom, our shellcode. We said call back to our current IP address on port 443. So that should be, if everything works right, that should be what it calls back to. So now when I run this, if everything works out correctly, I'm going to get a shell prompt there. If not, then I have to go back and look at my look at the Windows debugger and find out what the problem is. So cross your fingers. Nope. Got a shell. And I am user, right? Because user is running it. So now our original target was not our Windows machine. Our original target was Brainpan. So now that I know that this exploit works, let me exit this. Let me go back here. Brainpan was 111. I shouldn't need to change the port. The port should be the same. Let me save that. Let me listen again. And now when I run the exploit, now it's hitting the Brainpan, which is 111. So what should happen is I should get a shell on that one. Nope. That's interesting. Okay. Can you?
Brainpan's a Windows machine.
Well, actually, so Brainpan is not a Windows machine. It is a it's an Ubuntu machine, but it's running this in Wine. So it's a little bit, yeah, it's kind of weird because we've been doing it. So that's why like Who Am I didn't work, right? Even though Who Am I is part of Windows, so it's going to be a little bit different. So from here, this would be the point where you would try to escalate privileges, or if you're just trying to practice buffer overflow, you'd be done, right? Any questions? So I'm going to review this. I'm going to go over this again. But any questions before we start reviewing things on what we just looked at?
Will you be posting the recording?
Yeah, I can post that. That's no problem.
you.
So let me, it's a lot. There's a lot of different steps, and it's complicated, and it takes practice as well, right? So it's don't think we talked about this one time and you should be able to do this. Absolutely not. But I want you to have gone through it once, and I want you to understand the concepts, because these are the same concepts every time you hear, hey, they found an exploit for this app or this app. They're doing something similar to this, right? So again,
So does the Brainpan machine also have further steps to escalate privileges and whatnot?
I think so. I don't think I ever escalated privileges because I just wanted to practice buffer overflow, but I'm pretty sure it does, right? So here are our steps. get a copy of the application. Now, depending on, you know, for most of the capture the flags that you guys will do, they'll just give you the copy and say download it. For other ones, you might have to do regular ethical hacking type stuff to get it, like we just did. Basic things, looking at web pages and finding a downloadable. They're not going to make you do a really complicated, you know, thing before you even start the buffer overflow, right? So yeah, your regular scanning and enumeration. Once you have the copy, load it in Immunity Debugger. Now, if it was a Linux app, then you would be using DDD or GDB or, you know, some Linux debugger. There's a million Linux debuggers that basically do exactly the same stuff that we just did in Immunity, right? So it's the same process. It's just a slightly different tool, right? So you load it in Immunity Debugger and then fuzz it, right? Now to fuzz it, you're gonna need a proof of concept like the one I just sent you. Guess what? That will work on almost every one. The only difference is sometimes there'll be a little bit of code that it sends you first that you have to throw away, or there'll be a little bit of code that you have to send it kind of as a, you know, as a lead up. It'll, you know, for example, I did one, it was on a Linux vulnerability on some game that they had. And you had to send it, the game expected a left parentheses and then 17 dashes, and then your command, right? So everything had to start with that, right? But your fuzzer, which will be written in Python, will let you do that. Or you can start by using Netcat and just typing it in, but eventually you're gonna have to use that code. Luckily, everybody uses that same code I just sent you. It's the same for everybody. Hold on, let me. You know, so this has to be done in Windows. I've never used Ghidra to do anything like this. So I don't know, and I'm sure there is a Windows GDB too. So I don't know. I don't know if you could use, you know, it has to be running on the target system so that you can debug it, right? Because the debugger allows you to look at the individual spots in memory, look at the registers and all those things. So it has to be actively running. So if it's a Windows application, it has to be in Windows. And Immunity is the one that everybody uses on Windows because it works well and it's free. But you could theoretically use other ones. So you're going to fuzz it. And then once you fuzz it, then you're going to use Msf pattern create and offset to find exact number of bytes to the instruction pointer. Go ahead and extend that a little bit. Right? So you got to know exactly how many bytes the instruction pointer, right? Once you know that, then you're going to check buffers, right? A times offset plus B times 4 plus C times buffer. Once you have that nailed down, you know how much space you have, then you are going to check bad characters. And you're going to use exactly the array I sent you, right? You're just going to send that. Then once you know the bad characters, you're going to generate shellcode. Because you need to know the bad characters, so you know to remove them from your shellcode with the -B option. Once you've generated the shellcode, then you need to find the jump ESP command. That's going to be the command you find for all your easy ones. For more complicated ones, you might need to, make, or you might need to add something to a register or change the value. You might need to find a different command. But for all your basic ones, all the ones that you guys should be focused on, jump ESP is what you find. Address. And then you put it all together. Start a listener. Go. And once you get it to work in your test environment, then you change the IP address to your target machine and you hit it there. I know.
I have a question about the JMP,
I know.
the jump ESP address. So you did like jump ESP in Linux though on your Kali machine, and that will just translate to the same jump in address in Windows.
What I did was the MSF NASM shell, right? So this is the command I used. And so that tool, so just like you have the MSF pattern, offset and create, Msf Venom, this is a tool from Metasploit to make it easy to generate shellcodes. And this one, the shell allows me to type in assembly instructions, and it will tell me the numbering for those, right? That's what it's telling me there. Now, this is for Intel machines. If you had a different architecture, it'd be different. But like I said, everything you guys do, it's going to be Intel machines. And it's all going to be 32-bit. Does that make sense, Vince?
I guess so. That MSF NASM shell, I guess it's like a database lookup. Like, oh, okay, since it's the same.
Exactly.
It's the same.
Exactly, because it's always the same.
Okay.
Exactly, because it's always the same.
Okay.
And let me go back to the whiteboard. Hello, Artemis. Can you come back in a few minutes? Thank you. And what we're doing kind of internally is, right, we're filling up some space with our buffer. Right, so we're filling up some space with just the offset to the actual instruction pointer, right? And then we are writing in our EIP address. And then we're writing in our shellcode. Okay. Over here, we're going to have our ESP, which should point to this. And then we're going to have our EIP, right? Which we're going to make point to our jump ESP instruction. Oop, wrong thing. Come on, killing me. So by overwriting, right, the EIP address with that, whatever that jump ESP address, where basically it will tell the CPU, hey, your next instruction is over here. The CPU will load that instruction and says, oh, that's a jump to ESP. Let me check the value at ESP. Oh, that's the shellcode address. Let me jump down there. And then it starts executing our code. Does that make sense? In the cosmic sense of things? Or do people have questions? Okay. If you are like, this doesn't seem as painful as I thought. Let me do. Oh, hold on. Nope. Let me get this right. There we go. All right. Now let me bring this up here. All right. So if you're so inclined, and if you're on Try Hack Me and you go to Learn and you search for use BOF, there is a few different buffer overflow here. This is the one that is most like what we've been doing. Or maybe this one, actually, I'm not sure. One of these two. Actually, Tiberius. This is the one you want. So this buffer overflow prep is a great place to practice. The pseudo buffer overflow is actually a different type of buffer overflow attack, right? That is, it's not over a network. The pseudo buffer overflow is one that you can use to escalate privileges, right? That's the one they're talking about. And this one I haven't seen before, so I don't know this one. So this might be good too, but the one by Tiberius is excellent. So that would be a place you could practice. And he does take you through pretty much step by step. Yeah, he pretty much takes you through step by step. And if you got a little confused or something, you can go and look at the write-ups for that one. So that would be the place to get more information on buffer overflows. Whew. That's a lot. Drinking from the fire hose today. Anybody have any questions?
I think it's a lot to digest.
It's a lot. It's a big area. You know, it does. It's like I said. It's cropping up more and more in capture the flags, and it is a thing that I think you should do, like the Try Hack Me. And I don't think you need to be a master at buffer overflows, right? But because those concepts come up over and over again in weaknesses and vulnerabilities of all other kinds of applications, that is why I think it is kind of worthwhile to have some familiarity with it. Oh, so Ghidra does not debug, it only decompiles. What was, let's see. The other thing I wanted to ask you guys about, and we had talked about this before. Has anybody looked at CTF time at all?
No.
So let's take a look at it while we're here. So upcoming events. So today is the 8th, and next weekend is the 14th and the 15th. There's a one-day MoleCon. We're not doing one in Russia. I don't trust those people. MoleCon might be interesting. So top 5 teams go to, let's see what this is. So this would be, so this starts on Friday. Let's see, do they have examples of challenges? No, they don't have examples of challenges. No limit on teams. That's a good rule. So this one looks kind of like it's like in our lane. Let's look at this DCTF. These guys have a great icon, I got to admit. I don't know what DragonSec is. What kind of crazy flag regular expression is that? See, they have challenges. They don't have a scoreboard. They do have teams. So this one doesn't, it does say teams. So do you guys want to do one of these next week? Or are people like, it's the end of the semester, head down, I just want to plow forward?
I really want to, but honestly, all of my classes are coming to a head. I mean, so I could say that I'll do as much as I can, but I'm all my classes, the projects are coming due, so it's been starting to be a little tough.
So tell you what, I'm going to, it doesn't look like there's a registration limit for either of these. I think actually MoleCon kind of looks, but I just like the way that they have their stuff organized. So I'm going to post a thing in the Slack, and I'm going to ask for people to, if they're interested and which one they would be interested in. So check them out. Maybe go to their Discord channels and talk to them a little bit. If you guys are interested, let's say by Wednesday, you should reply to my post in the Slack and say, I'm interested, I'd like to do this. And if all we can do is, it's a 48-hour competition, but if all we can do is an hour on Saturday, then that's what we do, right? We don't have to do everything. yeah, you don't got to do everything at 60 miles an hour. It's okay to walk sometimes. But that's a thing that we could do between now and the end of the semester. Everybody with me?
Yep.
All right.
Once I get involved, it's hard to let go.
Yeah. So, you know, maybe you just stay away. That's okay too. All right, guys. Have a great week. Let me know if you need anything.
This has been great. Thank you.
Professor, have a good weekend. Everybody too.
Thank you. Oh, Professor, will you be posting it on Slack?
Yeah, I'll be posting this on the Slack. Yes.
Okay, thank you.